Welcome to the Phase Space Invaders podcast, where we explore the future of computational biology and biophysics by interviewing researchers working on exciting, transformative ideas. Today, my guest is Ariane Nunes-Alves, a group leader at Technische Universität Berlin, who is renowned for her work on methods and applications for the estimation of kinetics of ligand binding and unbinding. We often think about biology in terms of affinities and free energies, and of course, it's a convenient and well-defined framework. But there are important problems in the field of drug design that require optimizing binding kinetics rather than affinity. And it's an interesting challenge that cannot so far be addressed, for example, with structure-based AI tools or even coarse-grained simulations. So we start the conversation by asking how well the current atomistic models can even predict the rates of dynamical processes, given that our force fields are rarely explicitly parameterized to realistically model such time-dependent processes. We also discuss molecular crowding, another element that is usually missing from our models that nevertheless largely affects the behavior of molecules in a cell. Then Ariane makes the point that nowadays a significant portion of a PI's work consists of social interactions, be it with fellow computational scientists, collaborators, group members, or students, and that this should be reflected in the focus of hiring committees. Finally, we wrap up the discussion by wondering if our community still has a social platform to coalesce around, and whether that's something we could work on. Lots of questions ahead, so let's not wait any longer. Ariane Nunes-Alves, welcome to the podcast.
Thank you for the invitation. Yay.
So Ariane, when I think about the drug design people, a lot of them seem to be thinking of molecular interactions in terms of affinity, or how strongly things stick together. And it kind of makes sense because it's such an easy target, such an easy objective to define for your drug design pipelines. But you're the one who exposed a kinetic-centered view, right? So explicitly thinking in terms of the time it takes to bind or unbind. And so can you give us your take on why this is important? Why this question makes sense, perhaps what inspired you to look into it, and how we can even start to approach it as computational people?
Well, a lot of questions in one. So first of all, why this is important. So binding affinities, they are related to equilibrium properties, which is okay for in vitro experiments. But then when we think about the in vivo setting or about our cells are no-equilibrium systems. They are out of equilibrium. So if we are in equilibrium, we are dead. And then the best way to describe, not the best way, but a more reasonable way of describing no-equilibrium systems are kinetic parameters like association and dissociation rate constants. And then the other thing is that it's usually easier computationally speaking to study equilibrium properties like predicting, dissociation constants, because we can predict them by only looking at the end states, the bound and unbound states. Now, time scales, they depend not only on the bound and the bound states, but they also depend on the pathway we use to move from one to another. So this makes the problem way more computationally demanding. And I think that's why I went into this area, because I really like investigating pathways for binding and unbinding. Yeah, I think it's cool.
I think it can be rewarding looking at all the movies that were produced of these processes. The question could be, because my idea is that many of the models that we have were actually modeled to reproduce exactly the equilibrium properties, right? So what confidence do we even have that the kinetics that we have in the physical simulations are realistic?
That's a fantastic question. Yeah, so what I always try to do in my research, at least, is to reproduce experimental data. And in this sense, we have experimental kinetic rates, experimental dissociation or association rate constants for surface plasmon resonance or other experiments. And what I mostly use nowadays is tau range, developed by my former boss, my postdoc boss, Rebecca Wade. And in tau range, we can reproduce not the absolute values, but the relative kinetic rates for a group of compounds. And that's what gives us confidence that we are capturing the important biological detail there. But something that I think it would be very interesting to do is to come up with ways to verify that we actually have the correct pathways. I honestly don't know a reasonable experiment that can show us whether the pathway we see in the simulations corresponds to what we would see in experiment.
I can imagine that being done for like really, really large complexes where you can have a few probes and the pathway is taking kind of many nanometers, right? But not in a single binding pocket.
Yeah.
Because most of the time we'll get some equilibrium properties or time average properties of the system anyway. Yeah, that's a great challenge. So yeah, how do we trust the result just based on what would be a single number, right? The dissociation rate, for example.
Mm-hmm.
Do you have any ideas for how to move forward with that? Or is it something that the experimentators will have to figure out?
Yeah, I have no idea. Yeah. But I guess, as you said, if you have a system with a longer tunnel, for instance, where we can maybe engineer metastable states, we could think about designing some mutants that will just perturb the ground state and at the same time stabilize another intermediate state. Yeah. I wish I could convince someone to do it, but hard to convince experimentalists of my molecular dreams, but yeah.
That's definitely a lot of work. Yeah, more work than the actual scientific work. The convincing part. Yeah, so for example, what are the biological cases where this actually made a difference? If you can bring up some projects in which this question of optimizing kinetics made an impact in the biological problem.
Oh, sure. So there are a few papers that show, for instance, that for some specific systems, people have seen that the residence time, which is the inverse of the dissociation rate constant, is better correlated with in vivo efficacy than equilibrium properties. That's one thing. There is this consortium before here in Europe between pharmaceutical companies and universities called KFRDD, Kinetics for Drug Discovery. And they had also some examples where increasing the residence time or increasing the time the drug is spent bound to a specific protein, they could have a stronger effect for a specific drug, for instance, or in another case, they actually wanted to reduce the residence time because if the drug spends too much time bound to the protein, this would lead to undesirable side effects.
Right, so very case specific, yeah? That's what the bottom line would be. Yeah, if you think from the drug's perspective, right, there's a moment where you enter the cell and perhaps at some point you bind to your target and then you bind to something that tries to metabolize you and that's when you're gone, right? So it really makes sense through this lens how those properties can.
Yeah, if you look at the cell environment, it's actually a very crowded system with a lot of different macromolecules like nucleic acid, like you study, or proteins, and then there is a lot of opportunity for off-target binding or binding to an enzyme that will degrade you. So ideally, it would be good for the drug to have a fast association rate constant towards its target protein because then it binds fast and then it can also offset the competing molecules that also want to bind there. Yeah.
All right, that's a great point. Do we have ways to simulate that? Are we taking that into account?
Yeah, so I think the next step for not only for protein ligand binding, but for biological phenomena in general, to go in the direction of simulating more realistic cellular environments. And this is something I want to do, but yeah.
Do we have even a template for that? Like if someone wants to simulate typical human cytoplasm, can you just take a data set of, what would be the typical components and put them all together? That would be actually an interesting project if it doesn't exist yet.
Yeah, so I remember that in JCIM, maybe 3 years ago, someone made a publication there to set up the environment to simulate the cellular cytoplasm. And actually nowadays we do have the information we need because we have a lot of proteomic data available, and then we know which proteins are available in the cell and the amount in which they are available. So in principle, the work is possible, but in practice, it's very challenging because you have to integrate a lot of this proteomic information with structural information from the protein data bank or get models from AlphaFold 2. And also, when you set the system or the model, you have a very, very large system, and then how do you simulate it? So people usually simulate a piece of the cytoplasm and not the whole thing. Yeah.
Would have to be a selection.
And I'm currently writing a review about it together with Rick Kiagers from New York. So yeah.
Amazing. Yeah, it would have to be some sort of selection of average property proteins, right? But it would be awesome if one day, instead of putting just a box of water, you could put a box of cytoplasm inside your simulation model.
This would be very cool, yeah.
Yeah, and see how all that affects what we thought is just a kind of silly equilibrium property or kinetic property of a system we're studying. Because I don't know if you know of many cases where exactly people try to apply this approach and it changed things drastically. Are you aware of such cases where, where we saw the effect of environment in a simulation making a huge, huge contribution to the quantity of interest, whatever that was?
I have never seen such studies. No, I'm lying. There was a recent publication from Michael Feig in Nature Communications where they didn't actually simulate the whole cellular environment, but one way of simulating, of mimicking the crowded cellular environment is to use just one type of protein crowded in a high amount. Then let's say you can mimic the excluded volume and in some sense also the weak interaction that the proteins or the ligands will have with the crowder, that in this case is just one type of protein. And then as a model crowder, they used bovine serum albumin, and they saw that in the crowded environment, the binding pathway between an inhibitor and kinase changes. This is a very interesting result.
All right, that sounds very, very cutting edge. My point is those questions are really fascinating from the point of view of the point that was made many times before on this podcast, which is we're trying to approach the biological, right? We are starting to get past the phase of reproducing in vitro environment where everything is controlled and maybe there's just a PBS buffer and going to the wild west of the cell. Right?
Yeah, that's how I feel about it. The cell is currently the wild west. There are a lot of opportunities.
Yeah, we had a conversation with Pilar Casio, for example, where she mentioned in situ cryo-EM tomography that actually shows you how crowded this whole thing is, and people are trying to place proteins in their actual positions discovered experimentally. And I think that can be kind of synergistic with what you are describing, right?
Yes.
So many interesting frontiers there emerging these days. Okay, now from the sciencey to the social. So you pointed out, and again, that's in line with other discussions we've had here, how important the interpersonal skills are when evaluating potential hires for a faculty job, right? And we actually first met at a social event, so perhaps we've got it checked.
Yes.
But is scientific collaboration at the core of your argument, or are you making a broader point that goes beyond just scientists working together on various problems?
Oh no, my major concern when I made this point is that from my experience in Brazil and also here in Germany, I see, so first of all, now that I am a junior group leader, I see that a huge part of the job is actually interacting with people. So I think I say to my students every week that this job of professor or group leader is a job for extroverted people because you really have to talk to other people. And I'm not an extroverted people, to be honest, but I think I can manage social interaction. But my main concern when I said this is that I think a major part of the job is teaching and supervision. So we interact a lot with people to teach them and to mentor them. And I am kind of shocked or upset with the amount of stories I hear of PhD students or master students which were yelled at or treated poorly in whatever way. And I think this greatly comes from the fact that when people are selected for this group leader or professor position, people just look at the scientific achievements and they don't really care whether people will be able to deal with and manage other people. And I think this is a very important part of the job, because at the end of the day, we are here to serve and to teach people, younger people, and then
Right. It definitely doesn't get communicated in the stereotypical image of a professor, right? The stereotypical professor is usually kind of introverted. Although, as I also pointed out before, people back in the day, you look at the Solvay conference or all the famous interactions between scientists, they were interacting. They were not that introverted. So even this public perception is kind of cute in strange ways.
Yeah, I think the public perception is the genius scientist alone in the corner writing equations or investigating something alone, but it's so far from reality. You really have to later on communicate your science, discuss with other people. So this is another part of having interpersonal skills. So
Right, and enough to look at the Twitter biophysical community to realize that people are actually quite extroverted, and at least the people who self-select to go there, right? Maybe it doesn't apply universally. There's definitely a bias. But the whole question of community, I am trying with this podcast to create a feeling of community that, we scientific people are trying to talk to each other and bring up common topics and find common themes. But how do you envision the community? We have it now so divided into different platforms, into different subgroups. Would you say there is such a thing as the biophysical computational community?
Really, that's a difficult question. I think we could be together a bit more, for sure. But I feel like when we go to conferences, for instance, you and I, we were in the European Biophysical Society last year. I think there is a friendly community, at least among people in our generation. So,
Right.
But I think the podcast, for instance, is a great idea. People were a bit more active on Twitter before, but now with Elon Musk, I feel like things were diluted a little bit, and we still haven't found the place to get together again.
That's part of my concern, that some people left for Mastodon, some people stay on Twitter, some people left social media for good. And it was my general question, where do scientists meet if they don't, for example, go to a conference at a given moment?
Yeah, so I tried Mastodon and I found it hard to find new people. I tried Blue Sky and it didn't catch up with me yet. My PhD students are younger than me. They are talking a lot about LinkedIn, but I've seen it a couple of times and I don't really like the self-promoting vibes, to be honest, but I may end up going to LinkedIn. I don't know.
I think it's hyper-professionalized, so I don't really see LinkedIn as a replacement for Twitter in that aspect, right? Reddit would be closer, but Reddit is also for much younger folks, I feel. I already feel a bit
I've never used it. Okay.
But I know that there are, for example, bioinformatics communities, but they're mostly for students, people looking for advice, and more like undergraduates than the professional level. Yeah, it's a really tough question, I think, and one we could be paying more attention to. I don't know if anyone has any good ideas in that regard, but I really feel that the demise of Twitter was a bad moment for the biophysical community.
Yeah.
But then, it's really interesting what you say about the ultra or the hyper-social aspect of the life of a professor. Do you think it's also depending on the culture, or it's something that's universal? You have background from quite a few institutions, so.
Yeah, I think that's the professor life, yeah. I don't think that would change a lot across different countries. I think that's the way things are probably supposed to be.
All right. So, wonderful. Ariane Nunes-Alves, thank you for the illuminating discussion and for being on the podcast.
Thank you for the invitation. Pleasure. Yeah.
It was great. Hope you have a great day.
You too.
Thank you for listening. See you in the next episode of Space Invaders.